Greedy algorithms are a powerful approach to solving optimization problems, characterized by making locally optimal choices with the hope of achieving a global optimum. Unlike dynamic programming, which may involve solving multiple subproblems, greedy algorithms focus on simplifying the process by making decisions step by step. However, these algorithms are not universally applicable, as their success depends on specific properties of the problem at hand. To illustrate this, we will explore problems where greedy algorithms excel and identify the criteria for their correctness. Starting with the activity selection problem, we will see how the greedy approach efficiently selects the optimal solution. Later, we'll discuss the theoretical basis of the greedy strategy, such as the greedy choice property and optimal substructure, and extend the discussion to applications like Huffman coding and offline caching. Greedy algorithms work effectively when two key characteristics are present: the greedy choice property and optimal substructure. The greedy choice property ensures that a locally optimal decision leads to a globally optimal solution. This allows us to make decisions step by step, focusing only on the immediate problem. For instance, selecting the shortest path in a graph at each step aligns with this property. Optimal substructure implies that an optimal solution to the overall problem can be constructed using optimal solutions to its subproblems. This characteristic supports breaking down a problem into smaller parts and solving each one independently. Combining these two principles allows greedy algorithms to outperform more complex strategies in problems where they are applicable, such as the fractional knapsack problem and Huffman coding. The activity selection problem exemplifies the effectiveness of greedy algorithms. Imagine scheduling events in a single conference room to maximize the number of non-overlapping activities. Each activity is defined by its start and finish times, and the objective is to select as many compatible activities as possible. The greedy approach simplifies this problem by always selecting the activity that finishes the earliest among the remaining options. This strategy ensures that the room is freed up for subsequent events as soon as possible. The implementation involves sorting activities by finish time and iteratively selecting compatible ones. This efficient method reduces computational complexity compared to other strategies, such as dynamic programming. The recursive greedy algorithm for the activity selection problem systematically selects activities to maximize compatibility. The algorithm, denoted as recursive activity selector, works as follows. Starting with the first activity that finishes, it recursively selects the next compatible activity, continuing until no further selections are possible. This recursive structure exploits both the greedy choice property and optimal substructure. By focusing only on the earliest finishing activity, the algorithm minimizes conflicts, while the recursive calls ensure optimal solutions for the remaining subproblems. The pseudocode highlights the algorithm's elegance and efficiency, achieving an optimal solution in linear time when activities are presorted. The iterative version of the activity selection algorithm, Greedy Activity Selector, simplifies the implementation by eliminating recursion. The algorithm starts by selecting the first activity and proceeds sequentially, adding activities that are compatible with the previously selected ones. This approach mirrors the recursive version in logic but is more straightforward and often preferred in practice. By iterating through the sorted activities and maintaining a list of selected ones, the algorithm efficiently determines the optimal schedule. Both versions demonstrate the practical and theoretical strengths of greedy algorithms, providing a foundation for solving more complex problems. Greedy algorithms and dynamic programming are two prominent strategies for solving optimization problems, but they differ significantly in approach and applicability. Greedy algorithms make decisions in a top-down manner, selecting the best choice at each step based solely on the current state, aiming for simplicity and efficiency. However, this approach may not always guarantee a global optimum if the problem lacks the greedy choice property. Dynamic programming, on the other hand, is a bottom-up approach that evaluates all possible choices to ensure an optimal solution. It is more robust, capable of solving problems where greedy algorithms fail, but it often comes at the cost of increased computational complexity. Understanding the strengths and limitations of each strategy is crucial for selecting the right approach for a given problem. The knapsack problem illustrates the contrast between greedy algorithms and dynamic programming. In the 0-1 knapsack problem, where items must be taken as whole units or left behind, dynamic programming is necessary to explore all combinations and ensure an optimal solution. This problem lacks the greedy choice property, as selecting items with the highest value to weight ratio may not lead to the best overall result. In the fractional knapsack problem, where items can be divided into smaller parts, the greedy strategy works perfectly. By prioritizing items with the highest value per unit weight, the solution can be achieved efficiently. This difference highlights the importance of problem properties in determining whether a greedy or dynamic programming approach is appropriate. Huffman codes provide a classic example of a problem where greedy algorithms excel. Huffman coding is a method for lossless data compression that assigns shorter codes to more frequent characters and longer codes to less frequent ones. This approach minimizes the total length of encoded data, achieving optimal compression among all prefix-free codes. The greedy construction of Huffman codes begins by repeatedly merging the two characters with the lowest frequencies into a new node. This process continues until a single root node represents the entire tree. The result is a binary tree where each character's depth corresponds to the length of its code. This efficient, step-by-step process demonstrates the power of the greedy approach in real-world applications. Let us consider an example to understand the efficiency of Huffman coding. Suppose we have a dataset with 6 characters and their frequencies. The character A appears 45,000 times, while the character F appears only 5,000 times. Using a fixed-length code with 3 bits per character, encoding the dataset would require 300,000 bits. However, Huffman coding reduces this to 224,000 bits by assigning shorter codes to frequent characters, such as A, and longer codes to less frequent ones, like F. The process involves constructing a binary tree where each leaf node represents a character and its frequency. Traversing the tree generates variable length codes, such as A being represented by a single bit, 0, and F by 4 bits, 1100. This example highlights the practical benefits of greedy algorithms in achieving significant savings in data storage and transmission. The Huffman algorithm follows a well-defined sequence of steps to construct an optimal prefix-free code. Starting with a priority queue of characters and their frequencies, the algorithm repeatedly merges the two nodes with the smallest frequencies. Each merge creates a new internal node, representing the combined frequency, and the process continues until a single tree is formed. The final tree represents the optimal encoding, with code lengths determined by the depth of each character's node. This step-by-step merging process exemplifies the greedy choice property, as the algorithm consistently selects the most optimal pair of nodes at each step. By leveraging priority queues and efficient tree construction, Huffman coding achieves a time complexity of big O of n log n, making it both effective and scalable. The execution of the Huffman algorithm involves 4 main steps. First, we initialize by creating a leaf node for each character and adding it to a priority queue. The frequencies of the characters determine their priority, ensuring that the smallest frequencies are always selected first. Next, during the node merging step, we repeatedly extract the two nodes with the lowest frequencies and merge them into a new internal node. This process continues in the tree construction step, where internal nodes are created until a single root node remains in the queue. Finally, we generate code words for each character by traversing the tree, assigning 0 to left edges and 1 to right edges. This systematic process ensures that Huffman codes achieve optimal prefix-free compression. The correctness of Huffman's algorithm is supported by 2 key properties: the greedy choice property and optimal substructure. The greedy choice property ensures that merging the 2 least frequent nodes at each step is a safe choice that leads to an optimal solution. This is because any optimal prefix-free code must merge these 2 nodes without affecting the overall cost. The optimal substructure property states that an optimal solution to the overall problem contains optimal solutions to subproblems. In Huffman coding, the tree built from merging nodes optimally represents a smaller problem, and adding this result to the overall tree guarantees optimality. These properties provide a solid theoretical foundation for the algorithm, which has been proven correct through inductive reasoning. The time complexity of Huffman's algorithm is big O of n log n, where n represents the number of characters. This efficiency is achieved by leveraging a priority queue for managing node frequencies. Initially, the priority queue is built in big O of n time. During each merge operation, the algorithm performs 2 extract min operations and 1 insert operation, each taking big O of log n time. Since the merging process involves n-1 iterations, the total complexity of these operations is big O of n log n. This makes Huffman's algorithm highly efficient for constructing optimal prefix-free codes, even for large datasets. Huffman coding finds applications in various domains, thanks to its ability to achieve efficient lossless compression. In file compression, it is widely used in algorithms such as gzip and pzip to reduce file sizes while preserving data integrity. Similarly, in image compression, standards like JPEG and PNG incorporate Huffman coding to encode pixel data effectively. Beyond compression, Huffman coding is valuable in data transmission, where it minimizes the bandwidth required for sending information over networks. Database systems also benefit from Huffman coding, as it compresses records and indexes, optimizing storage and retrieval processes. These diverse applications highlight the versatility and practicality of Huffman coding in real-world scenarios. Despite its strengths, Huffman coding has limitations that must be considered in specific contexts. One limitation is the distinction between static and adaptive coding. Static Huffman coding requires the character frequencies to be known in advance, which may not be feasible for streaming data. Adaptive versions address this issue but add complexity to the implementation. The compression ratio of Huffman coding depends on the frequency distribution of characters. For datasets with uniform character distributions, the savings may be minimal compared to other methods like arithmetic coding, which can achieve better ratios in such cases. Additionally, the need to transmit the code tree along with the compressed data introduces overhead, which can offset some of the compression gains. In conclusion, Huffman coding is a powerful and versatile algorithm for lossless data compression, achieving optimal prefix-free encoding. Its applications span file compression, image processing, data transmission, and database systems, showcasing its impact across various domains. However, it is essential to recognize its limitations and explore alternative techniques when necessary. Methods like arithmetic coding or adaptive Huffman coding may be more suitable for specific scenarios. Overall, Huffman coding remains a cornerstone in the field of data compression, balancing efficiency, simplicity, and theoretical robustness.